So far, in our chemistry class, we've been working to better understand the atom. It turns out, to continue our investigation of the atom, we need to actually understand light better. And that's just what we'll do in this lesson. We're going to take a look at what light is, and we're going to learn to calculate things like its wavelength and frequency. Let's learn. In order to understand light, we have to understand waves. Waves are just something that oscillate. So here we see ripples of water. And if I just tracked one ripple, that ripple would go down and up, down and up, down and up, like an ocean swell. And so an ocean swell is, of course, another example of something oscillating up and down. And that's what a wave is, something that oscillates up and down. Okay? Now, if we have a wave that does this over and over again in a nice repeated pattern, we can describe it in a couple of ways. We could describe its amplitude. So its amplitude, which is right there, is like its height. So for example, in our water waves, that's just how high the water waves rise each time. So for example, if you hear that there are 4-meter swells, really big waves, that's just telling you the amplitude of the water as it goes up and down. Now, there's another variable that looks a little more confusing, and that's this lambda down here. Lambda is a Greek letter. You can remember that this has to do with waves because it kind of looks like a wave. Imagine that's like this ocean wave cruising forward, right? And that means wavelength. So that has to do with wavelength. And that's the distance between two peaks. So here's a peak and here's a peak. And that distance between those two peaks is called the wavelength. And we could have a wavelength for ocean waves or for light waves. For any sort of waves, we can have a wavelength. And so what we're going to do in this video is learn to think about light, which is a wave. But if we've been thinking about water varying up and down, when we come to light, what's varying? What's going up and down? And that's what makes light relatively confusing, because what's varying when it comes to light is an electric and magnetic force. What in the world does that mean? Well, we've actually already seen an electric force in this class, so let's remind ourselves of what that is. Remember in the oil drop experiment, we had an oil drop that was positively charged. And we said, hey, if the plate below it was negative, it was going to be attracted down to that negative plate. And the plate above it is positive, which was going to push it down also towards the negative plate. So that positively charged droplet was going to be attracted down below. Now imagine that you all of a sudden just switch really rapidly between a positive plate up top to a negative plate. So now you make this the negative one and you make this the positive one. Okay, well now the droplet is going to switch directions and it's going to start going up. Okay, well now imagine that you switch it again and then it's going to start going down. And then you switch it again and then it starts going up. Okay, that would be an oscillating electric force. Back and forth, back and forth, back and forth, back and forth. All right, and if we imagine this oil droplet that's charged sitting right here next to this electric force, it would rise and fall with the passing of our light. So light is an oscillating electric and magnetic force. And we're going to really focus on the electric force, which is the dominant component of light, though both are there. The electric force pushes and pulls on charged particles. So light shakes charged things. So one way to think about the way your vision works is that when light comes into your eye, it jiggles the electrons that are in your eye. And you perceive that as light, which is pretty crazy, right? But that's what light is, an oscillating electric and magnetic force. When we think about that force that's being described by the amplitude, a higher amplitude is just going to be a stronger force. So where is the force strongest on this wave? Well, the force is strongest right here. And then it's a little lower here. It's a little lower there. It's actually 0 right there. And then it flips in the opposite direction, pointing down, down, down. So that's a way we can visualize what's going to happen to a charge that we put in the way of this wave. It's going to be pushed up, 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 down, 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 up, 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 down, down, down. And for a brief little time, it's actually going to have no force on it at all. So the higher the amplitude of our light, the stronger the force. So if you really want to get charges moving, get a really big amplitude. Now, how do we experience amplitude? Well, actually, the bigger the amplitude light has, the brighter it looks to us. Okay, so the light looks brighter. If you see a really bright light and a really dim light, the difference between those two is the amplitude. Now, one thing we need to keep in mind with light, just like our ocean waves can travel forward, our light waves travel forward. And they actually travel really, really, really fast. So this c here is a variable we're going to see throughout our video. It's always equal to 3 times 10 to the 8th meters per second. That's how fast light travels in a vacuum in outer space. It turns out the speed of light actually changes as the light enters into, say, the atmosphere of our Earth or into water. But in a vacuum, it's always 3 times 10 to the 8th meters per second. That's super fast. It's 300 million meters per second. It's moving so fast that it takes only 8 minutes to get from the sun, this is our favorite image of the sun, to Earth. Just 8 minutes. Okay? Now, what that tells you is that if I just were to stand still and let light pass by me, there's a relationship between the wavelength and how often I see one of these peaks. So we're imagining that the distance from here to here is how far the light travels in 1 second. And if I have a really short wavelength, I'm going to see peaks very often. And if I have a really long wavelength, I'm going to see peaks less often. We call the frequency with which we see peaks frequency, which, totally makes sense, right? It's how frequently there is a peak. What doesn't maybe make sense is that we symbolize it with this guy, which is a Greek letter, the Greek letter nu. Okay, so when you see that, think frequency. That's actually one of the big challenges students have when dealing with light, is learning to recognize all of those different variables for what they are. And that little weird Greek letter nu is for frequency, how often there's a peak. So let's think about that again for 1 second. Imagine that you're standing right here and the light's traveling by. If you look up here, you have a very low frequency wave. And so if I counted how often there was a peak, it would be like peak, 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 not very often. But if I look down here where I have tons and tons of peaks because of my short wavelength, the frequency would be more like peak, 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 tons and tons of peaks every single second. And that's actually an important note. When I measure frequency and report frequency, I do it with the unit of hertz. So frequency has the unit of hertz, which is abbreviated Hz. And it's the same thing as per second. Let's talk about why that makes sense. That might seem a little weird at first, but if we're talking about how frequently something happens, per second makes total sense. For example, maybe I'm talking about how frequently your heart beats. And maybe when you're exercising, it beats twice per second. Okay? And if we're talking about how many waves go by, I'm just going to count the peaks and tell you how many go by in a second. So in this top picture, if we have 1, 2, 3 peaks that go by in a second, we'll say it's 3 hertz. This next one is 6 hertz, and this last one is 12 hertz. So that's just a way we can refer to the frequency. Now here's the thing, as the wavelength gets longer, the frequency gets smaller, as we've already discussed. And so there's an inverse relationship. That means as one gets bigger, the other gets smaller between wavelength and frequency. A short wavelength means a high frequency. And we actually have a mathematical equation that relates those two. Remember, right here, we have frequency. And right here, we have wavelength. And right here, what's that c mean? Oh, that's right, speed of light. And it makes sense that there's a relationship between the speed those waves are moving at and how often you see a peak, right? And so we can calculate, if we're given frequency, the wavelength. And if we're given wavelength, we can calculate the frequency. And those are inversely related. So if I have a really, really big wavelength, I have a small frequency. And if I have a really, really small wavelength, I have a high frequency. Okay, let's actually do this. Let's use that mathematical equation for a calculation. Now, here are some rules that I have for solving any problem. No matter what problem you have, start by writing down what we are given and include the units. That's always a good place to start. Then write down the variable you want. So a lot of students, when they get stuck on an exam, they kind of go with the sit there and stare at it approach. This turns out to not be very effective. If you just start to write down what you have, it will key off things you've learned and you'll start to learn how to solve it. I've sat down to tests where I haven't known how to do anything and I've started to write stuff out and ended up doing okay on the test. So writing down what we know, what we're given, and what we want is really helpful. And it's basically just going to solve the problem for us in this case. So let's do that. This problem tells us that green light has a wavelength of 5.3 times 10 to the minus 7 meters. And it wants to know what's its frequency in hertz. So we know the wavelength. That's what the first thing that was given to us. In a quantitative problem, that means problems with numbers, we can just go variable by variable, and we can start with the first number we're given and say, oh, okay, that's wavelength, and I remember that that weird lambda thing is wavelength, and then it tells me what the wavelength is, 5.3 times 10 to the minus 7, so I'll write that down. And now I need to make sure I put my units, which are meters. It comes right after the number. Cool, that's straightforward. And then it wants to know the frequency, so it wants to know this thing. All right, cool. And now I say, okay, what pieces of information do I have to help me? Well, I also know the speed of light. That's always something that we'll have, and it's always the same for this equation. So what that means then is we're going to write down frequency equals c over lambda, and now all we have to do is plug that set of variables in. So we know c is 3.00 times 10 raised to the 8th divided by 5.3 times 10 to the minus 7. This is the first time in this class we're doing a relatively involved math problem. And what I want you to do whenever we do this is have a calculator with you and punch it in as well. Make sure you get the same thing as me. Here's the thing, calculators can be tricky. And you'll notice I've put those numbers in parentheses, and that's actually what you want to do. You need to put those numbers in parentheses to get out the correct answer. And so put that into your calculator with parentheses, and you should get out that the frequency is 6 times 10 to the 14th hertz. Whoa, that's a big number. Remember, in scientific notation, when I write 10 to the 14th, that means there's 14 zeros after that 6. So that's a really, really, really big frequency. And that's because our wavelength is really small and light moves really, really fast. So it's a really high frequency. Now, you might ask the question, how many digits should I report here? Totally reasonable question. We're going to talk about that in more detail later in the class. For now, just write 1 or 2 digits and that'll be great. You also always want to make sure you have units. Okay, let's take a look at calculating now wavelength. This problem tells us that cell phones use light in the form of radio waves to communicate, and that radio waves have a frequency of around 1 times 10 to the 9th hertz. And it says, what is the wavelength of a radio wave? So let's once again write down what we know. We know that the frequency is 1 times 10 to the 9th, and its units are hertz. What are we looking for? We know we're looking for wavelength. What are the units of wavelength going to be? They're going to be meters, as we'll see at the end, because our speed of light has meters in it. Okay. I mean, this problem, if you pause for a second, is pretty cool. It's telling us that radio waves are just light, right? And that's true. All sorts of things around us that we might not realize are light are actually light. Radio waves, microwaves, infrared waves, ultraviolet light, visible light. And here we're going to figure out the wavelength. So now we'll realize that we have a little bit more work to do, because when I write my formula down, I see what I want is down here. And so that means I have to do some algebra to get it by itself. Here's a good rule. If what you want is in the denominator, that's the bottom half of our fraction, as a first move, always just take it up top. So don't worry about getting it by itself yet. Just take it up top and make your life a little easier. So we're going to multiply both sides by lambda. All right. When I do that, the lambda divided by lambda cancels out, and I get lambda times nu equals c. Okay, and now that I've taken that lambda out of the denominator, and now it looks much more pleasant. When it's a fraction, it looks kind of scary. Now I can think, okay, what algebra do I need to do to get wavelength by itself? I need to divide both sides by nu. Another tip here on the algebra, you always do the opposite thing that's being done to your variable in the equation. So I want to get wavelength by itself. Currently, it's being multiplied by frequency. So if I divide it by frequency, that'll get rid of it. All right, let's write our final equation over here. We have wavelength equals c over nu. The nice thing is every single time you use this equation, that's going to be the same exact algebra you need. Okay, now let's plug in our variables. Lambda is equal to 3 times 10 to the 8th meters per second. And then we're going to divide that by our frequency, which is 1 times 10 to the 9th hertz. Remember that hertz is actually 1 over seconds. And so what happens is our 1 over seconds up top and our 1 over seconds on the bottom end up canceling out. And so what's left is just our meters. We'll talk more about those units as we go through the class. So if that seems a little weird to you, don't worry about that. We'll keep working on it. Okay, what's our answer? Well, it turns out that our wavelength is 0.3 meters. Wow. So that is a really large wavelength compared to the last problem. And the last problem, we had something that was like a millionth of a meter. Now we have something that's a third of a meter. So radio waves are actually really long. Okay, let's sum up. Here's what we've learned about light. Light is a rapidly moving, varying electric and magnetic force. So this is where our speed of light comes in. So that's C. And it's varying like all waves. What's varying or oscillating is the electric and magnetic field. It has an amplitude, which we symbolize with an A, that tells us the brightness. It has a wavelength, which tells us distance from peak to peak, which we use lambda to indicate. And it has a frequency, which is how often there is a peak, which we use the Greek letter nu to indicate. It turns out both wavelength and frequency are different ways to tell us the color of light if we're in the visible range. Okay, so that's light. Next, we'll turn to using that to understand the atom. Hey, hey.